Alright, so I think I'm recording. Let's take a look at this next problem. We are looking at polynomial functions. We are trying to find the x-intercepts of the graph of these polynomial functions, and also they have different words for the x-intercept. They might refer to the x-intercepts as the zeros of the function, because if you're on the x-axis, the y-coordinate is 0, and the output of the function is, the y value. So when they talk about the zero of the function, they mean the values, the input values that cause an output of 0, that cause the function value to be 0, so they just call it the zero of the function. They may also call it the roots of a function. So x-intercepts, zeros, and roots of a polynomial function are all asking you, talking about the same thing. The a sub naught is just the notation, because of that you don't know what degree it is. There's only 26 letters of the alphabet. Well, this n could be, a very large value. It could be to the 100th power, or that exponent could be, conceptually it could be ridiculously large. Well, there's not enough letters. That when you studied quadratic functions, we just use ax squared plus bx plus c. There's only three, we only had three, so we just kept it easy and said a, b, and c. Well, rather than a, b, c, and then, when you get to the end, when you get to z, when you get to the end of the alphabet, you turn around and call it a, and then go through a, b, a, c, and then you get through the end. You can see that it's a little bit better if you just call all of the coefficients a and use an index that matches the exponent. A sub n is the coefficient of the term, the x to the nth term. A sub n minus 1 is the coefficient for the n minus 1th term. A sub 1 is the coefficient for the term with degree of 1. So when they say a sub naught, they just want the constant term. So we want to look at the factors of this 13. 13 is a prime number, so we've got plus or minus 1 and plus or minus 13. The factors of a sub n, the leading coefficient, 4 is a composite number, but fortunately for us it doesn't have a lot of factors, because when this list is long, it just creates a little bit more work for us in searching for the x-intercepts. So my factors of my constant term are my possible numerators. So if I use first a denominator of 1, then I've got 1 over 1, and I've got 13 over 1. Now if I use a denominator of 2, I've got 1 over 2 and 13 over 2. And now if I use a denominator of 4, I've got 1 over 4 and 13 over 4. So there's my list of possible zeros. We're not saying that these are the actual zeros of the function. We're saying that if this function has zeros, and if those zeros are rational numbers, then they'll be in our list. It doesn't say anything about if our zeros are irrational numbers, and it doesn't help us to provide a way to find those irrational values. So now, to find the actual zeros of this function, we either plug in these numbers into the function and look for 0, or use synthetic division and look for 0 as a remainder. So let's jump in and try to do these. If we make sure that your polynomial function is in standard form, and that there was not a greatest common factor, or otherwise when you generate this list, it's not going to work. You need to first look to see if there's a greatest common factor among your terms before you identify the constant term and the leading coefficient. Alright, so we can see that this is not 0. So 1 is not a 0 of the function. It is not an x-intercept. What about negative 1? many of you could probably have enough algebraic, enough a number sense, good enough at arithmetic that you may not have to go painstakingly through every number. You may be able to jump around and simply find the values. So I don't know what 13 times 76 is, but I can see that's not going to be 0, so I'm going to stop. Oh, I may have multiplied that previous number. 4 times 3 is 12. Oh, 52. Gosh. See, I told you I wasn't very good at. Oh, yeah, deck of cards. 13, 4, 52 decks, 52 cards in a deck. And this. Uh, and then this guy is going to be a positive value, but it's not positive 13, so 13 is not there. So I put off doing the fractions, so I'm going to have to go through and do the fractions. You can't hear it for some reason. I guess it's good that you can't hear it, but I listen also online to the radio while I'm doing these, and I've got Bob and Tom on right now, and there's a comedian that's making me laugh while I'm doing this. Although you can't, I can hear it in my headphones, but you can't hear it, or I hope you. I should double check. I hope that you can't. Hey, we found one. So let's. I brought the 4 down. Half of 4 was 2. I added those together, 26. Half of 26 was 13, and we found a 0. So now in factored, since 1/2 was an x-intercept, in factored form, that's x minus 1/2. But we want to write this as 2x minus 1. Let's see. If you set this equal to 0 and you multiplied both sides of this equation by 2, then distribute the 2 to both terms. 2 times x, I've got 2x. 2 times negative 1/2 is negative 1. Half of 2 is 1. And 0 times 2 is 0. So when I see a fraction like that, we write it in factored form like this. So what this is telling me, this original quadratic function, 4x squared plus 24x minus 13, I have found, using this rational zero theorem, that 2x minus 1 is a factor of that. And now from my synthetic division, no? I'm a little bit surprised. Maybe I've done something wrong. I should pause the video. This 4x plus 26 are both even numbers. There's a common factor here, but there wasn't a greatest common factor in my original. Oh, because I multiplied it by 2 right there. Okay, never mind. So in factored form then, I can see that I can factor a 2 out, and I've got 2x plus 13. And when I go to solve this, I have 0, 2x minus 1 times 2 times 2x plus 13. Well, when I divide both sides of this equation by 2, these 2's cancel, and 0 divided by 2 is 0. So I just get these factors, 2x minus 1 and 2x plus 13 are the only contributions towards making this product equal to 0. So my x-intercepts for this are x equals 1/2 and x equals negative 13/2. Alright, so let's look at our factoring method. Since this was a quadratic, we already had the skills. We didn't actually have to use this rational zero theorem and the remainder theorem and factor theorem and synthetic division to do this. We could just factor, or we could have just simply used the quadratic formula, and the quadratic formula would give us the same result because that's a quadratic equation. Alright, so let's do this in a different color. Had we just jumped in and said 4x squared plus 24x minus 13, if we set that equal to 0, and for this x method, you draw an x over the middle term, multiply the first term times the last term, and get negative 52x squared. Two values that multiply together to give us this negative 52, but add to give us a positive 24, are positive 26 and a negative 2. If I double the 26, with this being negative, I get negative 52, and if I add these together, I get 24. So if we come in and put this in the form of a table with the first term and the last term going along one diagonal, and the values that you found in your x, the values that you found here and here going in the other diagonal, if we look here, 13 divides both of those numbers. If we look here, these numbers are relatively prime, but well, other than they're both negative, so we'll use a negative 1, and positive 13 times a negative 1 is negative 13. So these are both even numbers, and they both have an x. So I have 2x. These are both even numbers, and they both have an x, so this is 2x. So let's check it real quick. 2x times 2x is 4x squared. Positive 2x times negative 1 is negative 2x. 13 times 2x is 26, and we already checked that 13 times negative 1 was the negative 13. So this table now allows us to factor, and we get the same answer that we did over here, that this guy factors to 2x plus 13 times 2x minus 1. And so that first factor gives me, if I subtract 13 and divide by 2, and here if I add 1 and divide by 2, so I get the same the same answers, the same zeros of the function. If using, I have building a lot of confidence now in this theorem and in this technique of synthetic division, because I know it's working, because when I compare it for something that I know for sure certainly works, factoring, or I could have done the quadratic formula, right? If I would have came in, suppose I didn't recognize that this factors, if I'd come in and use the quadratic formula, take the opposite of b, which is negative 24, plus or minus the square root of b squared, which is 24 squared, minus 4 times a times c, all divided by 2a. Underneath the radical, the discriminant, we get, well, what do we get? $784, and if we take the square root of 784, we get 28. So when we subtract these, when we have negative 24 to negative 28, give me a negative 52, and 4 divides both of those. And then if I use addition, 28 minus 24 is 4, and 4 over 8 reduces to 1/2. So even if with this quadratic equation, had I used the quadratic formula, I still would have got those same x-intercepts. Alright, so I hope that helps.